Hi, everybody. I'm sorry I'm starting a little bit late today. I hope everybody's doing well. So just to not recap, go over what we have this week. Today, we will finish chapter 10. Chapter 10's pretty short, especially compared to chapter 9. We're just going to see how to treat activity coefficients for ionic electrolyte solutions, pretty much just at low concentrations. And that's today. We have a problem set out there. Hopefully that's going okay. I've answered a question or two about that and the extra credit, which is due Friday. And then on Wednesday, we'll have the exam. And I'll be here during class time to answer questions if you have them. I guess what we'll do is record that normally. I don't know if everybody's just planning on coming and seeing what happens or working on the test during class or whatever. I don't want people to feel like they're going to miss anything if they don't come or whatever. Does anybody have any questions? Let's see, what do we got here? 7, okay. All right. So last time we talked about symmetrical electrolytes and how you can measure the activity. Let's see. The activity coefficients and the activity of these solutions in general. The one thing that is a little bit unusual, and you might have to think about it a little bit, is that the activity coefficient for an ionic solution, or the ions in this electrolyte solution, is always less than 1, at least at these moderate concentrations. 1 mol is fairly concentrated, especially for electrolyte solution. So the activity is less than 1. Let's think about what that means. And let's think about what it would mean like for a gas, right? So if we think about the activity or the activity coefficient for a gas, the vapor above a solution, right? If the activity coefficient for a vapor above the solution is less than 1, it means essentially that less of it is vaporizing than we would think. Less of it is vaporizing compared to an ideal system, right? So something's holding it back. For the ions in solution, what this means is that their activity, their non-ideality, is less. The activity is less than an ideal solution, and it's not like a lot less, right? It's between 50% and 100% if you look at these numbers, 0.5 to 1. And we've talked a lot about expecting electrolyte solutions to be non-ideal, which is true. The forces are very strong, but that might make you think that since the forces are so strong, that the effect is really strong too. And that's not the case. And that's pretty weird if you think about it, that the activity is damped, but not in a positive direction and not strongly in a negative direction. It's really kind of moderate, which is pretty, it seems pretty weird to me, right? Ionic forces are strong. Why isn't the effect strong? It's much less than the effect that we see for a mixture on the effect of the vapor, right? The vapor, we see very strong non-ideal effects most of the time. So this is pretty weird. And that's one of the things I want you to think about physically, why that is today. So last time we talked about symmetrical electrolytes like sodium chloride or magnesium sulfate. And let's generalize now to non-symmetrical electrolytes. What we need is the molalities of the positive and negative ions. How do we get that? Well, you can say the molality of the positive ions is the stoichiometry of the positive ions times the molality of the electrolyte itself, and likewise for the negative ions, right? So if you think about magnesium chloride, the molality of the chloride ions is twice the molality of the compound, but the molality of the magnesium ions is the molality of the compound, and that just comes about by that coefficient that we defined. And we also want to define or remember the total stoichiometry, right? So for magnesium chloride, this factor would be 3. MgCl2. Okay, so let's look at a solution of a single electrolyte, the general case, or of course this should reduce to the symmetrical electrolyte. Let's start with the Gibbs additivity equation, which basically just says the total free energy is the weighted chemical potential of each. And of course, we're going to break the electrolyte into its ions, which we can do using the just previously mentioned definition of their concentrations. Right? Okay, I have to decide which way I want to look at this. Okay, but hold on, I made one little mistake here. We want to put this in terms of the free energies of the ions themselves, not the solute, right? So we have that. All right, and then so what we can say is that the chemical potential of the solute then is the kind of the weighted free energy or chemical potentials of the two ions, depending on their stoichiometry. Okay. So if you're the kind of person who's going to go through the notes or the book and kind of redrive everything, right? I think that's a really good thing to do. I understand not everybody's going to do it, but I think it's a really good thing to do. So if you go through and do this the same way that we did it for the symmetrical case, you end up with this expression. Remember, we want to put this in terms of the field or the potential inside the solution, right? So we have the chemical potential of the positive ion and the chemical potential of the anion, right? And for each part, this is the zero field part. So we're going to group those together. And the field dependent part, which depends on their charges. Right. But again, the neutrality condition dictates that this weighted sum of the charges equals 0, right? So that means that field dependent term goes away again, and we're left with a relatively simple looking expression that doesn't depend upon the field. Whoops, 0, right? If we collect all the various parts together, as we did last time, this includes the reference and so on, what we end up with is this expression. Whoops. And of course, the complexity is inside the log. We get the stoichiometry part. I'm going to bring this over here to have more room. We have the positive activity coefficient, the cation activity coefficient, the anion activity coefficient, weighted by the stoichiometry. And then we also have the concentration part. All right, so what we've basically done is the same thing as before. We've pulled out the individual concentrations of the ions and made it just dependent on the concentration of the solute as a whole, right? Because that's easy to measure. We know what that is. So what we're trying to do here is turn this immeasurable thing into something we can measure. Again, we're going to use a mean ionic activity coefficient as before. But this time we have to be a little bit more careful with it because of the different stoichiometries that are possible in general. Oops. One over a new. Right, so remember that this summed activity coefficient is that. Okay. And so what we also have is that the reference, this is kind of the same as before, the reference of the solute, the chemical potential reference of the solute is just the weighted sum of the chemical potentials of the ions. And this is at 0 field. All right. So what we see, again, that the chemical potentials of the ions depend upon the field, but the overall does not. So what this kind of means is that the gross effect of the field is 0. Individual ions will move with the field, but all in all, this kind of motion of the ions in the field is not what thermodynamics measures, right? That's kind of the way that I think about it anyway. All right, so what we end up with is this expression. It's pretty much the same as the symmetrical case. It just has the weights of the stoichiometric weights in there, basically, that part. Right. And this difference, remember, what makes this useful is this difference is measurable. Say from the relative fugacity measurement, which we talked about last time, right? Which means the mean ionic activity coefficient is available through measurement. And finally, if we want to write this as the activity, it turns out that at kind of this low level, looking at the solutions, we're not interested in just the activity, right? We're interested in what's under the activity, but we might then give this activity to other people who are interested in it in chemical reaction sense, which we're going to actually talk about soon. But we could, of course, write this in terms of the activity, which gives the very simple expression, very simple looking expression that. Right? So really the activity is everything in the square brackets. And what we're also saying is that this pressure factor is 1, because we're usually not concerned about that. All right, so the next thing to worry about is what if we have multiple solutes? This could be something like sodium chloride plus potassium acetate solution, or let's say sodium chloride plus magnesium chloride. So I picked these two examples, which we're only going to do one of them kind of a little bit specifically, but I'm trying to get you to think about. In the first example, we have 4 different ions. But in the second example, we have a chloride common ion. And the second example presents a little bit, not difficulty, you just have to be careful at a certain step. So I'll point that out. So what we have for each solute is the same expression right? We have this weighted average of chemical potentials. If we let B equal sodium chloride and C equal magnesium chloride, then we have something like this. We have the additivity rule, which gives us again, the weighted chemical potentials. In this case, we have 3. And if we just write out what we have NB times mu B of the sodium plus NB And actually, this is not right. That label is not right. And in this case, the only difference that we have is a factor of 2 because magnesium chloride has 2 chloride ions, right? These aren't exactly neutrality equations, but we also have these equations within each solute, right? The chemical potential of the B solute must be the chemical potential of the sodium plus the chemical potential of a chloride, and the chemical potential of the C solute must be the chemical potential of the magnesium plus 2 times the chemical potential of the chloride. So this is kind of an individual requirement. And these follow the kind of general expression where we had this. We could also separate activities into ion molalities if this is convenient. So if we're dealing with a mixed electrolyte, in order to kind of keep track of what's going on, we might break down the molalities into the individual ion molalities, right? If we have one electrolyte in solution, it's probably more convenient just to refer to the molality of sodium chloride or magnesium chloride. But if we have a mixture of these two, we might want to keep track of the sodium, the magnesium, and the chloride, since the chloride's coming from 2 places. So we might end up with an expression like this. We have, again, this pressure factor. Even though we almost are never going to consider this pressure factor, for completeness, I'm going to keep it in there. We have the mean ionic activity coefficient raised to the power of the total stoichiometry. But now we're going to break the positive and negative molalities up like that. So we could do that too. That could be a useful or important way to do this. So what you have to be careful about, though, here, this, let's say, is for sodium chloride, for example, right? So the label tells us it's for sodium chloride, and this is also for the sodium chloride, right? But this is going to include all the chloride, even from the magnesium chloride. So we get this kind of crosstalk between the ions, and it's not really a problem, but we have to realize that in a sense we lose some individualized information. In other words, for a pure sodium chloride solution, we couldn't even really do this, right? Because you can't increase the chloride ion concentration independently of the sodium. But since you have the presence of magnesium also, you're able to have this inequity between the sodium and the chloride ion concentrations, right? So that's going to change the mean ionic activity coefficient for the sodium chloride, right? Does that make sense? And at first it sounds like it's a problem, but on the other hand, this solution is what it is, and you can't really imagine, you can't really apply conditions of a different solution to the solution you have, right? You're actually accounting for that solution in a more accurate way. So it seems like it's a problem, but I don't think it is. All right, so let's look at the Debye-Hückel theory. And what we're going to do here is we're going to describe the physical situation, and also what's kind of unsaid in this part is Debye and Huckle observed the behavior and described the physical situation, and then they came up with the theory. Well, then we'll lay out the empirical equation that's used and we'll look at the limiting behavior of this, which turns out not to be super useful, especially these days where we can have computers do a lot of the heavy lifting for us, and we don't have to worry about, we don't have to worry about blocking a bunch of undergraduates in a room with desks and paper and pencils calculating numbers anymore, right? We can have a computer generate a lot of numbers for us now. Oh, shoot, I forgot one thing. Hold on a second, let me move this. Because I forgot what about ion pairs. Now, ion pairing occurs at higher concentration, right? So what this does in a strong electrolyte is it lowers the total concentration of particles, right? This is what is accounted for in a Van Hoff factor, which we haven't talked about yet, but you might remember it has to do with colligative properties. Or weak electrolytes, right? So both of these situations, let me write this down, both of these examples, there may be other examples that do the same thing. Both of these examples remove the relatively simple relationships between, let's say, the molality of the solute, the molality of the positive ion, and the molality of the negative ion. For a strong electrolyte, it's just a simple matter of applying the stoichiometry, and we know what these concentrations are. But if we have something like, I don't know, acetic acid, probably like the most generic example you can think of. Acetic acid is about 1 or 2% ionized in dilute solutions, maybe up to 5% ionized in dilute solutions, right? So instead of getting 2 moles of particles from a mole of acetic acid molecules, you get like 1.05, right? You get 1.05 particles for every 1 particle of acetic acid because of the incomplete dissociation. What this really means is that the mean ionic activity coefficient becomes less directly physical. It doesn't really change the use of it. You can either think about your molecular solute having its activity coefficient elevated in some way away from a neutral particle, or your ionic strong electrolyte ionic activity coefficient being highly damped, right? So it acts more like a non-electrolyte. So we can, from a non-electrolyte to some activity that involves the electrolyte, or the ionic activity coefficient approaching a non-ionic, right? And so in this case, sometimes this is called a stoichiometric activity coefficient, to distinguish it between something that's purely non-electrolyte and something that is an electrolyte. Because it's strictly still an electrolyte, but it is more ideal at higher concentrations, right? Because the number of ions that these things put out is much, much less. Okay. Debye-Hückel theory. So Debye-Hückel theory turns out to only consider, it only considers electrostatic or ionic interactions between ions. In other words, the thinking of the theory is that the interaction between the ions and the solvent is already accounted for with kind of the ideal dilute theory part of this. So this is still going to contain an ideal dilute limit inside of it, okay? We know these forces, these types of forces are quite strong. But they're screened by the solvent. Now, again, the screening by the solvent is really accounted for ideal dilute, D-I-L-U-T-E, right? So the screening by the solvent is really kind of wrapped up in the ideal dilute definition. But what maybe you don't think about is they're also screened by the other ions. All right, so let me give you two situations, right? Two possible schemes in solution. What if the ions in solution were randomly distributed, right? And so what I want you to think about is a random distribution of the ions is not going to be exactly like I'm going to draw, but it's going to be kind of what I draw. Most of the time, it's almost a checkerboard, right? Because you can imagine that balancing the randomness, right? Where you could say that a very simple idea for this, right, is to imagine like a chess or a checkerboard, and you have some positive ions and you have some negative ions, and you're going to put a positive ion or a negative ion on each checkerboard space just to model a bigger system. And every time you want to put one of these down, you're going to flip a coin, right? And if it's heads, you put a positive ion down. And if it's tails, you put a negative ion down, right? And you can do that all the way across. Okay, and you might want to balance this a little bit by electrostatics, right? Because there is a chance, it's a rare event, but there is a chance you might put down 10 negative ions in a row. It just might happen because of the coin flip, right? So it's random, but if you think about it, it's also going to be tempered by the electrostatics, right? So there's going to be like a faster return to 50-50. Does that make sense? Anyway, it's almost checkerboard. So you might imagine this, and in some sense, there's some overall balance of charge. But if you think about the way it works in reality, is you put a positive ion down, and this thing, because of the strong forces, attracts other negative, it attracts opposite ions like this. And a negative ion, and I'm thinking about now a positive ion all by itself and a negative ion all by itself. I don't want to try to fit these together. I just want to think about kind of an extreme. The negative ion is going to be surrounded by positive ions. So each individual ion will end up being surrounded by opposite ions. And this is, let me not call this reality, right? Because I said two schemes. So let's call this the shell model, right? So each individual ion will be surrounded by opposite ions. Now, probably at this point, you already know a little bit about how ions are solvated in water, right? If you have a sodium ion, the oxygen ends of the waters are going to be pointed towards the sodiums, and they're going to be pretty much stuck there. So what you end up with is like you end up with this big entourage of water, right? It's like all these hangers on, like 10 or 12 waters that always are just stuck to the sodium. So it looks like, it looks like when I go out in my yard and I haven't seen my dogs in six hours, I just end up walking around the yard with like 6 dogs hanging off of me, right? Or like when I have puppies and I'm walking around with the puppies, they tend to like bite your ankles. So you end up with like 3 or 4 puppies stuck to each leg as you're walking around, right? So it's kind of like that model, the shell model. You end up just with these things, the opposite ions stuck to it. And it turns out the shell model is more accurate to what we see, right? So the positioning, my pencil's really thick today. What's going on? Maybe I'm just pushing super hard today. Positioning of the ions is not random. Each ion will generally be surrounded by opposing ions on average. So what this does is it screens those charges, and the ions screen the charges much more strongly. I'm not sure I want to say effectively, but much more strongly than a polar solvent like water will do. So what happens is each chemical potential for an ion is lowered It's lower than you think it is. It's lowered compared to the chemical potential of the ion in a bare solvent. In other words, right, I love drawing cartoon pictures, so because I have to visualize them. If I have a sodium like this, right, and I have waters, let me write them as V's because that makes it pretty clear, the arrangement. We end up with something like this, and out here, you can still feel this positive charge. In other words, at some distance, I don't know, 3, 4, 5, 10 angstroms, let's just say 10 angstroms, you'd feel that positive ion more than if you had a sodium like this and you had some chloride ions, right? And you come out here the same distance. Because those negative ions are actually going to oppose that positive ion charge more, right? So here, the chemical potential in water is higher than it is there. So this qualitatively explains why the mean ionic activity coefficient is less than, but close to 1 in electrolyte solutions. And what I mean is that it's between, it's between 1 and 0.5. It's really kind of a moderate activity ionic activity coefficient compared to the activity coefficients of other real systems, right? It's kind of unexpected because the forces are so strong, right? So these individual ion activity coefficients become less than 1 as the solute molality is higher than the ideal dilute range. So they're kind of damped or limited. The particular example is figure 10.2c. Again, we looked at this at the very beginning. Right? That's this effect here. It's really kind of moderated, much more than you might expect if you thought about it in a vacuum. Okay, so that kind of explains physically the part of the theory. What is the theory? Let's just write the result down. The Debye-Hückel theory, undergraduates are never expected to derive this thing because it's a beast. It's just really, it's hard, right? It's even hard like for a graduate class. So we just usually write the result down. And we express this with the labeling variable I, but this is always going to be for the ion, right? So we have these coefficients. And it turns out to be dependent on what we call the ionic strength. So we have to define this, but it's something that makes sense. Okay, so let's write down what these are. The A's and B's are Debye-Hückel parameters, which depend upon the solvent and the temperature. So the temperature dependence is in that A and B, right? A is what we call the mean ionic diameter. Let me write this in red. This is usually taken as an adjustable parameter, but the numbers you get out of this, in other words, the sizes you get out of this are, let's say, picometers, right? So in other words, it's a real size, and it makes physical sense. It might end up being a little bit like the parameters in the van der Waals equation, which are also supposed to relate some sort of physical size or something like that. And most of the time they kind of make sense, but sometimes they don't. It's kind of like that with these two, right? They're kind of right in the neighborhood, but again, this is an empirical formula, so we can't expect it to be 100% logical. Okay, and what is IM? IM is called the mean ionic strength. Let me just remind you that we found a dependence on the square of the molality before, and kind of our simple treatment. What the ionic strength does is it breaks that actually down into the square effect comes from the charge, not necessarily strictly the molality, right? And that kind of makes sense because we know Coulomb's law is Z1, Z2, right? So Coulomb's law is on the square of the charge, and this kind of puts that, maybe my pencil tip is wearing out, I don't know. My pencil tip was a little bit unscrewed. I guess for some reason that makes it more flexible and makes it thicker. Okay, so it's the molality times the charge squared, right? So this is where that, another way to look at that square dependence on the charge. All right, so what if we have water at 25 degrees C? What we get for these parameters, the textbooks always define what the A's and B's are. In other words, they have a specific definition based upon physical constants. But again, I consider that at this point to be a detail. These constants depend upon the square root powers because of the square root dependency. .285 times 10 to the 9. All right. So the B is quite large, right? And that makes you think that the denominator is really a big effect. But again, we have to use SI units for all of these things, right? So if you look at the size of B, 10 to the 9, A is a diameter in meters. And if it's picometers, then that's like 10 to the minus 12, right? So already the A times the B is on the order of 10 to the minus 3. right? So that's actually not as big a denominator as we think. All right, let's look and see what this looks like. So here's the mean ionic activity coefficient of HCl. The solid curve is experiment. The dash curve is Debye-Hückel theory. Now I said the A is an adjustable parameter, right? But it makes sense. This is supposed to be basically the size of the ion, 5 angstroms. How big is a hydrogen atom? An angstrom, right? So that kind of makes sense. This is some sort of effective ionic radius. Maybe it's the range or the effect of the ionic charge, right? About 5 times the size of a hydrogen atom if it's a hydrogen ion or a chloride ion, right? The dotted line is the Debye-Hückel limiting law, which we'll talk about in a minute. But you can see, you can get a pretty good agreement all the way up to a 10th molal, right? And that's pretty concentrated for ions. So this is able to give a decent answer, right? So the theory, let's see what the theory predicts. The theory predicts, if you go in and put in numbers, that the mean ionic activity coefficient is less than 1 if the molality is not 0, right, which is what we see. And this mean ionic activity coefficient goes to 1 as the molality goes to 0, right? Again, that's what we need it to do. Okay. Okay, as all the solute concentrations go to 0, as all the solute concentrations go to 0, we obtain what we call the Debye-Hückel limiting law. And the denominator goes to 0. The BDH times A times that part goes to 0, and you're left with this. Just the top. Okay. And we have to use the absolute value of the charges because of that minus sign out front. Okay. That's that other dotted line in the figure. You can go back and look at that just so we know what we're dealing with here. Well, you can see why it's called the limiting law, right? Because you can't even think about using this until we're at extremely low concentrations, maybe 0.01 molal, and even at the top end of that, it's not very good, right? So you have to be extremely careful using the limiting law. And I would reiterate that I think the limiting law, there's no reason to use it. The only reason you would ever use it is to get yourself in the ballpark, because nowadays it's not hard to do the calculation, right? Even in Mathematica or MATLAB or whatever, you could set it up to get a bunch of numbers that you can then use. Right, so it's really only, you should really only consider it below 10 millimolar, and then only for symmetrical solutes, symmetrical electrolytes. Okay. All right. So finally, the last thing we're going to talk about in chapter 10 is getting mean ionic activity coefficients from experiment, and you do this with osmotic coefficients. For ions, we went through this last time, the kind of where this comes from. It's actually a relatively simple derivation, easy for me to say, right? But what happens is if we do this for electrolytes, remember on the top we get the difference between some chemical potentials. On the bottom we get something that we could just calculate. And the only difference here is now we have this stoichiometric factor which accounts for the total number of ions. And we no longer have a sum. So again, the nu is the nu plus plus nu minus. Right? Remember I said for this osmotic coefficient is really a measure of the physical effect of the number of particles. It's really a way to physically measure how the vapor pressure of something changes as you put a solute in it. And this will become even more physical and satisfying when we talk about colligative properties after the Wednesday. Okay, this is now the example of a binary electrolyte. Okay, so what follows here is a pretty quick derivation to get to the end, because I want to, because using this for electrolytes presents a kind of a mathematical problem, which I'll talk about in a second or two here. And again, the best way to be comfortable with this is to run through the derivation yourself. I think I made a little bit of a mistake here. Yeah, I did. Okay. So if you follow through the derivation that we did last time as applied to this electrolyte equation, really the major change is the introduction of the counting the number of particles here, the number of ions. Right, okay, so remember the trick here is we measure things in terms of the solvent, right? And we want to use a trick, Gibbs-Duhem, to get us the activity of the solute, right? There's that dependency. So what we do is we set up the two equations, and the big difference here is we have an electrolyte, so we have the mean ionic activity coefficient. But other than that, it looks very similar to what we had before. The way you convert back and forth is Gibbs-Duhem, d mu A plus NB d mu B, shows how the chemical potentials are dependent on each other. We also have, oh, that's not right. We have these two substitutions. I need to be very clear because handwriting really can mess you up, right? The number of moles of solvent times the molar mass of the solvent can be shown to be the same as NB over the molar mass of B, right? This is that approximation we talked about last time too. You make these two substitutions, and what you are able to do is you're able to say d log of the mean ionic activity coefficient equals d phi m plus phi m minus 1 over mb dmb. And so we end up with really the same kind of expression that we had before, just in terms of our mean ionic activity coefficients. Remember, this gives us the ability to measure the activity coefficient at some concentration MB prime, knowing the osmotic coefficient at MB prime. Remember, this is a measurable. We can easily measure this from vapor pressure or whatever. And then we have an integral part where we have to integrate this correction. The way you can think about it as a correction. Right, so that involves a numerical integration. Okay, the problem is the integral becomes difficult to integrate numerically as MB goes to 0, the slope goes to minus infinity, right? So in other words, if we kind of take a peek at what happens here, the slope of this function gets really steep. So this introduces large errors in this region, right? Because the steep's so sharp that if you're off a little bit, you're making a big error, and it's compounded by the logarithm. So this is a problem, and this is a problem that a mathematician would say, oh, this is really a problem, you shouldn't do this. But a chemist is going to say, well, I'm gonna get around this. So the solution is to split the integral. And basically what you're going to do is this, the activity coefficient depends on you getting the osmotic coefficient at that value, and then integrating something else up to that value. But what we're going to do is we're going to say, well, we have these osmotic coefficients. We could measure these very easily, pretty much as close as we want to this limiting value. So let's take advantage of that. Let's chop up the integral, right? And instead of integrating over this space, let's integrate this space, right? So what we're going to do is, even though that error close to 0 is quite high, the total value of the integral there is really small. So let's do as much as we can to the right, to the right of that limit, right? And minimize that closeness as much as possible. That's essentially what we're going to do numerically. So this is how you translate that into mathematical terms. You have this function, right, which is phi m minus 1 over mb, but we're going to split this up into some new region, which is closer to this limit. So this new molality, MB double prime, is a low molality where we may still measure the osmotic coefficient. And the mean ionic activity coefficient can be gotten by the Debye-Hückel equation. So we're doing two things. One thing is we're moving our integration region closer to this problem area, and the fixed point, that's right, and the fixed point over here where we stop the integration, we're going to use the Debye-Hückel law to get that value there, right? So we're really minimizing this error-prone region. So what this leads to, right, is that you get this expression. You get the mean ionic activity coefficient at the molality that we want, but you just get a little bit longer expression. This is the part that was the same, but now you have the value of the osmotic coefficient at this lower molality. You get the mean ionic activity coefficient that you measure from the Debye-Hückel law. And then you get this integral part. Right? And you're avoiding the zero entirely. You'll notice that -1 is gone, right? Because you're take that comes from the integration at 0, because you know the value there, right? So you just end up with two known quantities, the osmotic coefficient that you can measure, a part, right? A part of the mean ionic activity coefficient that you get from the Debye-Hückel law, which is pretty good, right? And then an integral part that's in between. So if we look at, I always need to kind of figure out what all this relates to. So what you're doing is you're finding the value here. You're going down here to a comfortably low region where you can get the activity coefficient, right? This is your integral. This is well behaved. So you have no problem doing that integration, right? It's a regular looking shape, nothing funny going on. And all this is accounted for here. And this is exaggerated, right? This is exaggerated because this is actually small. And actually what you're doing is that this part, this is now getting a little complicated. This part is this part. Anyway, if you come all the way up here, right? And you just tried to do this, the same way that the example, I think it's problem 11 in chapter 9. If you try to do that the same way as you would in problem 11, the integral part will just give you problems, right? It just kind of blows up. You can't find the value at 0 because it goes towards infinity. And so this is just a way to kind of move the bar over. Okay, so that's it for chapter 10. Here's what I advise you doing is, working on the problem set. And working on the problem set will prepare you for the test. You might want to work on the midterm plotting thing a little bit, but you might probably want to leave that till after the test. And then ask me questions today if you have any questions. I'll be around. I won't be farther than maybe a half hour from my email or whatever. So if you have questions, you'll be able to find me easily. Okay.